whenever your load spike has subsided, whatever it is that you want to determine as an administrator or as a decision maker or as the one who is responsible for running this infrastructure. This is something that you want to do at a time of your convenience and choosing. So while in high availability clusters it should be a no-brainer to automate failover, it's usually a really, really bad idea to automate failback. I say usually because there may be, conceivably, there may be some situations where this might make sense, but in the majority of the cases it does not. In the vast majority of the cases it does make sense to automate failover. In the vast majority of cases it does not make sense to automate failback. Now, in the event of failover, failback, we need to make sure a few things. So one thing is our failover and failback always has to be transparent to our clients. So that means that when our clients connect to the service and the service now runs, or previously connected to the service, and the service now runs on a different node, then the client must notice as little as possible of that. So ideally, this failover and failback must be completely transparent. Now, this can be done in a variety of ways, and for the most part, it's something that will just work. It will work pretty much automatically. So if we have, for example, an entirely stateless protocol, so we have, for example, a machine communicating with a highly available service over a UDP transport, which by definition is a stateless protocol, then one of these UDP packets will go to one node before the failover, and then some other UDP packet will go to another node after the failover. And because the application and the protocol as such is stateless and must handle that basically in stride, there's nothing that you need to do on the client side or on the server side. You will simply have an application which will do this transition absolutely seamlessly, provided that this service is bound to a virtual IP address, which is automatically taken over from one node to another. Examples of this would be DNS, which is UDP-based, or also NFS, which has a UDP-based variant. If you're dealing, the same thing would, by the way, also be true for an HTTP service, because outside of the single TCP session, an HTTP request and response is also stateless. So if we have a client whose HTTP request goes to one server first and gets a response from there, and the next HTTP request goes to an entirely different physical node, then the client really doesn't care, because it's operating on the basis of a stateless protocol. If, however, we have a protocol that is stateful, we need some sort of a retry mechanism. Thankfully, most TCP applications are, of course, built in with the network as not considered entirely reliable, so most of the applications will have, most of the applications that we do encounter, indeed the vast majority of them, will have an automatic retry mechanism. For example, almost all database client libraries have, when they communicate with the TCP-based service, will have such a retry mechanism in place. A MySQL client, for example, automatically reconnects as the server goes away. The same thing, to the best of my knowledge, is true for a Postgres client, and this is also true for many, many other services. This is also true, for example, for certain file services, etc., etc. So the good news here is that for the vast majority of applications, this client transparency, if we have a service that is bound to a virtual IP address which can move between cluster nodes, there's really nothing that you need to do about this. It will just work. However, in practice, we have also encountered some, I would say, legacy applications that really cannot handle a server going away. And there, it really makes no difference whether we're talking about a highly available service or whether, for example, the application was interrupted or restarted server-side. That is something that you really should no longer encounter in practice, but you still do. In our experience, and based on the consultancy work and support work that we do, we have most typically found this behavior in individually developed or in-house developed applications where some sort of software application was tailor-made to the customer's needs, and it was simply not part of the specification to handle this type of server outage. And in that case, that application may actually require a restart in order to reconnect to the service. As I said, in standard software and specifically in open source software, this is something that you typically do not encounter anymore, but there are some applications that you still find deployed out in the field, legacy applications that don't handle this well. In that case, they might require an application restart on failover, which can, however, also easily be automated. And what's also important to achieve fully transparent failover and failback is that it has to be transparent to the application itself. And here we're talking about the server-side application. So the server-side application must really not be able to tell whether it's running on one node or another node, or at least if it is able to tell, then it must not care. And the easiest way to do that, or the common and straightforward way to do that, is to simply make all of the storage that the application uses accessible from both nodes. And there are two ways to do that. The more conventional approach is what you can see on the left-hand side of your slide right now, and that is the shared everything approach. And the shared everything approach, both or all of the cluster nodes share one data silo where they basically store all of their data. That approach is a conventional one. It's been around forever, and it is certainly not without its drawbacks. So in the shared everything mode, the foremost disadvantage is, whilst we have full high availability and full redundancy on the level of the server hardware, we have zero redundancy on the level of data. So while we have full redundancy in terms of data node, in terms of server nodes, we only have one shared data silo. If that data silo goes away, becomes unavailable, gets destroyed for any reason, then basically all of our beautiful server high availability comes to naught. That might sound like an overly disastrous event. It really isn't. Think about, and I could tell you a lot of horror stories that we've heard happen to customers, actually, where even without physical destruction of anything at all, really, data storage simply became unavailable to literally all the nodes in the data center. Firefighters intervening, demanding that a specific generator be shut down for security reasons in the process of a fire or similar incident in a completely different part of the data center. Power outages, that sort of thing. So when that happens, you really have a problem. You also have a really, really bad problem in a different case, namely when you have two nodes that write to the same data in an uncoordinated fashion. And that is an event that is typically known as a split brain in clustering. Really, really bad thing, because in case you have a single data silo, a single instance of data, and you have several nodes basically overwriting their changes in an uncoordinated fashion, you need to bust out your backups, which typically means really, really, really bad downtime. So that's the shared everything approach. Not really the most state-of-the-art approach for high availability clustering anymore, because what we now have is the shared nothing approach. And the shared nothing approach means that rather than having a single shared data silo, we now have a replica of the data that is for exclusive use of each and every individual node.